Before we get into our work in the next set of videos, I want to talk about the differential operator. It's something that offers a notational advantage in working with expressions that contain derivatives. If we have y, which is a function of x, then the differential operator dy, this is how it's written, dy, represents the derivative of y with respect to x. And d2y, it looks like a d squared, but it's d2, is d2y dx2, the second derivative. So this uppercase d is just a differential operator that represents a derivative of a function. Something like y prime plus 5y can be written as dy plus 5y, and in shorthand, d plus 5 acting on y, right? So I have the d plus 5 in parentheses with the y outside of it, and it just represents y prime plus 5y. It's not quite multiplication, but it is d acting on y plus 5 times y, right? So there is a multiplication with the constant there, but d is a derivative. Given this expression, we can operate on it using d. And the result would actually just be to increase the order of each derivative. So d acting on d plus 5, which is acting on y. I'll be a little formal here, but we're going to skip in the work that we're going to do in our examples. But d acting on d plus 5 acting on y is d acting on dy plus 5y. That's going to be the second derivative, d2y, plus 5d, the first derivative, y. And we can represent that as d2 plus 5d acting on y. So the notational advantage is that we can increase the order of derivatives by applying the d operator to it, and it behaves as though it's distributing, although it's just differentiating each term. Further, we can operate on d plus 5y using d plus 2. The way that's going to work is it's d acting on d plus 5y plus 2 times d plus 5y. We already saw that the first one becomes d2 plus 5d acting on y. Multiplying by 2 just gives us this 2d plus 10 acting on y. And everything's acting on y, so we actually can pull the y out and end up with d2 plus 5d plus 2d plus 10. Well, that's d2 plus 7d plus 10 acting on y, and if you look at that set of parentheses, what's inside of it, d2 plus 7d plus 10, it's exactly what we would get if we took d plus 2 and acted on d plus 5y using that, right? So it looks like foiling, it's going to act like foiling, but I want you to know that that d represents a derivative and it's not quite multiplication. Now, part of where we're going to end up going with this is, suppose we have the equation y prime plus 5y is equal to like e to the 3x. This can be written as dy plus 5y equals e to the 3x, or skipping ahead a little bit, I don't know if I'm skipping anything, d plus 5 acting on y equals e to the 3x. Now, suppose, let me move this, I take that d plus 2 operator and I act on both sides of the equation, d plus 2 here and d plus 2 here. We've already seen what the left-hand side becomes, but mathematically what's happening is we're taking the derivative of the equation and adding to it twice the equation. Because we're doing the same thing on both sides of the equation, this is actually a mathematically legitimate process. The left-hand side, we don't need to change, but the right-hand side deserves a little bit of attention. Here's what's really important and I think useful to see, to remember that this is not quite multiplication. What the right-hand side actually represents is the derivative with respect to x of e to the 3x. That's the d part. plus 2e to the 3x. So this is going to be 3e to the 3x plus 2e to the 3x, which is going to be 5e to the 3x, of course. And your question might be, where did the d go? But remember, the d is the derivative. So when it's not being applied to y, where we just write d or d2 or something like that, remember that it's a derivative, and hopefully this will clear up questions that may come up in the examples we're about to get to.